Hello, everyone. Before I start, I just want to welcome everyone to this Molex 3D webinar on using simulation to optimize injection molding cycle time. In today's fast-paced world, reducing cycle time can save not only time, but also significant cost and resources. My name is Ziad Mizwi, and I'm an applications engineer here at Molex 3D. Today, I'll be walking you through the presentation, so let's get started. So this slide is going to mark the start of our introduction. Today, we're going to cover the basics of injection molding cycle time, and then we're going to focus on how to optimize filling, packing, and cooling time using simulation. So injection molding cycle time is made up of four main phases. We've got filling, packing, cooling, and mold open or ejection. Today, we're going to focus on the three stages that have the biggest opportunity for optimization. Those are going to be filling, packing, and cooling. The approach we're going to take is simple. So for filling, first we're going to look at the U-curve theory and the balance between shear heating and cooling. For packing, we're going to be looking at gate freeze time, as well as some additional factors that will affect pack optimization. For cooling, we're going to look at the time to eject as the key result. Filling time is only a small part of the total cycle, but it still matters. If we optimize every stage carefully, even the small gains we get during filling time can add up to meaningful cycle time savings overall. The first concept that we should understand is the U-curve. So here we have an XY plot with the injection time here on the x-axis and the required injection pressure here on the y-axis. And here we can see that on one side, if the filling is too fast or the injection time is too low on the left side of this curve, the shear heating is going to go up and the injection pressure is going to rise. On the other side, if filling is too slow, the material is going to lose too much heat to the mold. This is going to lead viscosity to increase and the pressure to rise again. The goal isn't necessarily always to make filling as fast as possible. The goal is to find the optimal fill time, where pressure demand is going to be the lowest and where the warpage risk is going to be reduced. It is within this process window that we'd like to optimize our filling. So there's a few useful rules of thumb for estimating fill time. First off, flow rate equals the volume divided by the filling time, and the filling time can be estimated as the maximum flow length divided by the injection speed. When the machine is not known yet, a typical injection speed estimate is around 100 to 150 millimeters per second, and 120 millimeters per second is a good practical value. So that is going to mean roughly 1 second of fill time for every 120 millimeters of flow length. So now that we've kind of covered those basic estimates, let's take a look at some more practical ways to judge the filling performance. The filling melt front time alone is not going to tell us whether the process is truly optimized. So the next step is to use the temperature result. Here we're going to use the temperature isosurface to evaluate the balance between shear heating and cooling. The isosurface is going to help us see the temperature distribution at a specific value, so we can inspect how the melt behaves across the part during filling.